Computer memory is the invisible force that powers every calculation, application, and process in your digital devices. Without it, even the fastest processors would be useless. But how exactly does this crucial component work? At its core, computer memory is a system that stores data and instructions for the processor to access. Think of it as a vast array of tiny electrical switches, each capable of being either on or off, representing the binary digits 1 and 0. These binary digits, or bits, are the fundamental building blocks of all computer data. Computer memory comes in several forms, each serving different purposes. Random access memory, or RAM, is your computer's short-term memory. It temporarily stores the data your computer is actively using, allowing for quick access to information needed for running programs. Unlike your hard drive, RAM is volatile, meaning it loses all stored information when power is turned off. Read-only memory, or ROM, contains permanent instructions that don't change, even when the power is off. These instructions are essential for starting up your computer and performing basic input and output operations. Cache memory serves as a high-speed bridge between the processor and main memory. It stores frequently accessed data to reduce the time the processor spends waiting for data from the slower main memory. Modern computers typically have multiple levels of cache, labeled L1, L2, and L3, with L1 being the smallest but fastest. How does a computer actually store and retrieve data from memory? Each memory location has a unique address, similar to how houses have street addresses. When the processor needs to access data, it sends the memory address to the memory controller, which then retrieves the data from that specific location. Memory is organized in a hierarchy based on speed, cost, and capacity. At the top of the hierarchy is the processor's registers, which provide the fastest access but have very limited capacity. Next comes cache memory, followed by main memory or RAM, and finally secondary storage like hard drives or solid-state drives. As you move down the hierarchy, access time increases, but so does capacity. This hierarchical structure is crucial for balancing performance and cost. If all memory were as fast as registers, computers would be prohibitively expensive. Conversely, if all memory were as slow as hard drives, computers would be frustratingly sluggish. Modern memory systems employ sophisticated techniques to optimize performance. Memory interleaving allows multiple memory modules to work simultaneously, increasing throughput. Virtual memory uses hard disk space to supplement RAM, creating the illusion of more memory than physically present. Memory protection prevents programs from accessing memory allocated to other programs, enhancing system stability and security. The evolution of computer memory continues to drive advances in computing power. From the magnetic core memory of early computers to today's high-density RAM modules and lightning-fast solid-state drives, improvements in memory technology have been fundamental to the exponential growth in computing capabilities. Understanding how computer memory works provides insight into one of the most critical components of modern computing systems. This invisible yet essential technology enables everything from simple calculations to complex artificial intelligence, forming the backbone of our digital world.